Hello friends, welcome back. In this video, we have to study the MO energy level diagram for the N2 and the O2 molecule. Now, in case of the N2 means the nitrogen molecule. There is an interaction between the S and the P atomic orbitals. That's why we have to follow the second figure, that is the figure B. While in case of the O2 molecule, oxygen molecule, there is no interaction between the S and the P atomic orbitals. That's why we have to follow the figure A. That is the first figure. So let's start with the first molecule, that is the N2 molecule. So how this N2 molecule is formed? So while drawing the MO electronic configuration, we have to put the 10 electrons. So from where these 10 electrons are coming? So the structure of N2 molecule shows presence of two nitrogen atoms. So we are having the first nitrogen atom with the atomic number 7. That means the electronic configuration is 1s2, 2s2, 2p3. Similarly, the second nitrogen atom with the atomic number 7. That means the electronic configuration is 1s2, 2s2, 2p3. Now here we know that the 1s2 atomic orbital, they are lower in energy and hence they are not used for bonding and hence known as the non-bonding. So while writing the MO electronic configuration, we have to use a letter K, and as there are two 1s atomic orbital, we have to repeat the letter K. Why K? Because these electrons, they are present in the first shell and the first shell is known as the K shell. So only the 2s and the 2p of first nitrogen and the 2s and the 2p of the second nitrogen, they are used for the bonding purpose. So we can say that the 2 electron from the 2s of the first nitrogen and the 3 electron from the 2p of the first nitrogen, total 5 electrons. Again, the 2 electrons from the 2s of the first nitrogen and the 3 electrons from the 2p of the second nitrogen. Total 5 electrons from the first nitrogen, 5 electrons from the second nitrogen, and these 5 plus 5 total 10 electrons. And these 10 electrons, they are filled in the MO energy level diagram. So we can say that the two 2s atomic orbitals and the 6 2p atomic orbitals of the two nitrogen atoms. That means there are total 8 atomic orbitals which results in the formation of the 8 molecular orbitals. Now here we know that the 2s and the 2p orbitals of the nitrogen atoms are close in energy. So they interact and the sequence of the energy level of the MOs is according to the second figure, that is the figure B. Then the 10 electrons are filled in the molecular orbitals by using the two rules. The first one is the Abbe principle and the second one is the Hund's rule of maximum multiplicity. So let us see the MO energy level diagram for the nitrogen molecule. So in the nitrogen molecule, the diagram is drawn across the energy axis, that is the increasing energy. At one side, we are having the atomic orbitals, at the other side also the atomic orbital, and at the center the molecular orbitals. The atomic orbitals, they are for the first nitrogen and the second nitrogen, whereas the molecular orbitals, they are for the nitrogen molecule. Then at the lower side, we are having the MO energy level diagram for the first, that is the 2s atomic orbital of first nitrogen and the 2s atomic orbital for the second nitrogen. As there are two atomic orbital, there should be two molecular orbital. The lower, that is the bonding, is the sigma 2s, and the upper, that is the anti-bonding, is the sigma asterisk 2s. Then the second MO energy level diagram will be for the 2p. 2p of the first nitrogen, 2p of the second nitrogen. Again, there are total 3 plus 3, 6 atomic orbitals. There should be 6 molecular orbital. Lower 3 will be bonding, upper 3 will be anti-bonding. So the degenerate pair is the pi 2py and the pi 2pz, and next is the sigma 2px. So these are the 3 bonding. Then second degenerate pair, that is the pi asterisk 2py and the pi asterisk 2pz, and the third one is the sigma asterisk 2px. So this is the MO energy level diagram when there is an interaction between the s and the p atomic orbitals. That means the figure A. Now let us see the filling of electrons. Now in case of the 2s, from each side we are having the 2 electrons. So this is the first electron and the second electron for the first 2s of the nitrogen. Again the first electron, second electron for the 2s of the second nitrogen. So total 4 electrons. So 2 are going in the bonding and 2 in the anti-bonding. So first 2 in the bonding, remaining 2 in the anti-bonding. While in the nitrogen, we are having the first electron, second, third, again first, second, third. All the 3 electrons, they are unpaired with the parallel spin. So total there are 6 electrons. So these 6 electrons, they are filled in the MOs by using the Hund's rule of maximum multiplicity. So this is the first electron in pi 2 py, then pi 2 pz, then again pi 2 py, pi 2 pz, finally sigma 2 px and the sigma 2 px. So these are the 6 electrons, they are filled only in the bonding MO. So this is the MO energy level diagram for the N2 molecule. So while writing the MO electronic configuration, first of all we have to use the letter KK for the 1s. Then next will be sigma 2s2, sigma asterisk 2s2, pi 2py2, pi 2pz2, sigma 2px2, pi asterisk 2py0, pi asterisk 2pz0 and the sigma asterisk 2px0. So let us see this. MO electronic configuration of the N2 molecule is KK, sigma 2s2, sigma asterisk 2s2, pi 2py2, pi 2pz2 and sigma 2px2. That means all the electrons, they are filled in the lower. So the stabilization energy, which is equal to number of electrons in BMO into minus beta plus number of electrons in ABMO into plus beta. In case of the BMO, that is the bonding 2 plus 2 plus 2 plus 2, total 8 electrons. And in ABMO, there is only the 2 electrons. So it becomes 8 into minus beta plus 2 into plus beta, which is equal to minus 6 beta. So this minus 6 beta value is known as the stabilization energy. Again, we know that when there are more number of electrons in BMO than the ABMO, then the molecule is said to be a stable molecule. So here there are 8 electrons in BMO and 2 electrons in ABMO. So it is a stable molecule. So we can say that here there are more electrons in BMO than in ABMO. The molecule is said to be a stable molecule. Next factor, that is the bond order, which is equals to 1/2 into number of electrons in BMO minus number of electrons in ABMO. So which is equals to 1/2 into 8 minus 2 and which is equals to 3. So it indicates that there are 3 bonds between the 2 nitrogen atoms. That means we can say that there is a triple bond between the 2 nitrogen atoms. So the structure of the N2 molecule is, we are having a triple bond between the 2 nitrogen atoms, and the triple bond indicates the presence of one sigma bond and the 2 pi bonds. So this is the structure of the N2 molecule. And finally, the magnetic behavior. In case of the N2 molecule, all the electrons are paired. The last entering electrons are paired. So we can say that it is a diamagnetic in nature. So this is regarding the N2 molecule. Now let's move to the second molecule, that is the oxygen molecule. Oxygen molecule. So how this oxygen molecule is formed? Oxygen molecule, while drawing the MO energy level diagram, we have to put the 12 electrons. So from where these 12 electrons are coming? The structure of O2 molecule shows the presence of 2 oxygen atoms. So we are having the first oxygen atom with the atomic number 8. That means the electronic configuration is 1s2, 2s2, 2p4. Again, the second oxygen atom with the atomic number 8 means the electronic configuration is 1s2, 2s2, 2p4. Again, we know that the 1s2 atomic orbital, they are lower in energy, and as they are lower in energy, they are not used for bonding, or we can say that they are non-bonding atomic orbitals. So as they are non-bonding, while writing the MO electronic configuration, we have to use a letter K. Why letter K? Because these electrons, they are present in the first shell, which is known as the K shell. And there are 2 1s atomic orbital, that's why the letter K is repeated. Then we can say that the 2s and the 2p of first oxygen and the 2s and the 2p of the second oxygen, only they are used for the bonding purpose. So from the first oxygen, 2 electrons from 2s and 4 electrons from the 2p. Total 6 electrons. Again from the second oxygen, 2 electrons from the 2s and 4 electrons from the 2p. 6 electrons. So 6 from first oxygen and 6 from the second oxygen. Total 12 electrons, and these 12 electrons are used in the MO energy level diagram. So we can say that there are 2 2s atomic orbitals and 6 2p atomic orbitals for the 2 oxygen atoms. Hence there are total 8 atomic orbitals, which results in the formation of the 8 molecular orbitals. After this, Here this point is important. The 2s and the 2p orbitals of oxygen atoms are well separated. So they do not interact with each other, and hence the sequence of energy levels of the MOs is according to the first figure, and the first figure is the A figure. Then the 12 electrons are filled in the MOs according to the first one Abbo principle, and the second one is the Hund's rule of maximum multiplicity. So let's see the MO energy level diagram for the oxygen molecule. So we are having the MO energy level diagram, which is drawn across the energy axis, the increasing energy at one side atomic orbital, another side atomic orbital, at the center molecular orbital. The first atomic orbital is for the first oxygen atom, second atomic orbital is for the second oxygen atom, and the molecular orbitals, they are for the oxygen molecule. At the lower side, we are having the MO energy level diagram for the first 2s of the first oxygen and the 2s of the second oxygen. There are two atomic orbital, therefore two molecular orbital. The lower, that is the bonding, is sigma 2s. Upper, that is the anti-bonding, is the sigma asterisk 2s. Then the next MO energy level diagram will be for the 2p of the first oxygen and the 2p of the second oxygen. There are 3 plus 3, total 6 atomic orbital, therefore 6 molecular orbital. Lower 3 will be bonding, upper 3 will be anti-bonding, and their symbols are sigma 2px, pi 2py, pi 2pz. These two are the degenerate. Again, pi asterisk 2py and the pi asterisk 2pz. They are degenerate. And finally, sigma asterisk 2px. So this is the MO energy level diagram in which there is no interaction of s and the p atomic orbitals. Now let us see the filling of electrons. Now in case of the 2s of both the oxygen atoms, there are 2 electrons. So this is the first electron, the second electron. Again the first electron, second electron. Total 4 electrons from the 2 oxygen atoms, they are filled. The 2 are first of all filled in the bonding, remaining 2 in the anti-bonding. So this is the first, second, remaining 2 anti-bonding first and the second. So this is regarding the 2s. While in the 2p, we are having the first electron, second electron, third electron. They are filled according to the Hund's rule. Then the fourth will be paired. Again first, second, third. Hund's rule. Again the fourth will be paired. So total there are 8 electrons. These 8 electrons, they are filled in the MOs. So what, first of all in the sigma 2px, pi 2py, pi 2pz with the parallel spin. Again in the pi 2py, pi 2pz. And finally pi asterisk 2py and the pi asterisk 2pz. So this is the MO energy level diagram with the electrons. Now, while writing the electronic configuration, first of all we are having the letters KK for the 1s, then it will be next sigma 2s2, sigma asterisk 2s2, sigma 2px2, pi 2py2, pi 2pz2, pi asterisk 2py1 and pi asterisk 2pz1. Let's see this. The MO electronic configuration of the oxygen molecule is KK sigma 2s2, sigma asterisk 2s2, sigma 2px2, pi 2py2, pi 2pz2, pi asterisk 2py1 and pi asterisk 2pz1. Then the stabilization energy, which is equals to number of electrons in BMO into minus beta plus number of electrons in ABMO into plus beta. In the BMO, there are 2 plus 2 plus 2 plus 2, 8. And in the ABMO, 2 plus 1 plus 1, 4. So it becomes 8 into minus beta plus 4 into plus beta, which is equals to minus beta. And this minus beta value is called as the stabilization energy. Again, there are more number of electrons in BMO than the ABMO. 8 in BMO and 4 in ABMO. Therefore, this molecule is said to be stable. Here there are more electrons in BMO than in ABMO, hence the molecule is a stable molecule. Then the bond order is equal to 1/2 into number of electrons in BMO minus number of electrons in ABMO, which is equals to 1/2 into 8 minus 4, which is equals to 2. It indicates that there is a double bond between the two oxygen atoms. So let us see the structure of the oxygen molecule. So we are having a structure like this. In between two oxygen atoms, there is a double bond. Double bond indicates there is a one sigma bond and one pi bond. So this is the structure of the oxygen molecule. Now finally the magnetic behavior. The electronic configuration, MO electronic configuration shows the presence of two unpaired electrons, right? And as there is a presence of unpaired electron, the molecule is paramagnetic in nature. So we have to study this paramagnetism of O2 molecule in the next video. Thank you. Thank you for watching this video.